All right, welcome back, everyone. Today, we're going to talk about something, well, something that might just change how you think about the beginning of everything. We're going way beyond the classic Big Bang story. So let's just jump right in. So let me just throw this out there right at the start. It's a question that kind of pokes at a story we've all heard a million times. What if that huge cosmic explosion, the Big Bang, wasn't actually the beginning? I mean, what if it was just a single chapter in a much, much bigger story? You know the story, right? It's almost become this modern myth. You've got this tiny, super hot, unbelievably dense little dot. And then boom, it just explodes, and out comes space, time, everything we see. It's an awesome image for sure. But, and this is a big but, it's got some really serious problems when you dig into the physics. And here's the absolute key to understanding this. Physicists call that dot a singularity. But here's the thing. It's not a real place. You couldn't, go visit it. A singularity is basically just a point where our math completely breaks. Our best equations, even Einstein stuff, just stop working. The answers all come out as infinity, which is basically the universe's way of telling us, hey, your theory is broken here. It's a warning sign, not an actual starting point. So what we have here is this huge difference, right? On one side, you've got the simple story, this cosmic seed that everything grew from. It's easy to picture. But on the other side, you've got the hard reality of the physics. And the physics says a point where all the rules go out the window, well, that's not a beginning. That's a dead end. So trying to build our universe on this idea of a singularity gives us three massive headaches. First up, there's this weird self-creation problem. How can the universe create itself? It's like trying to pull yourself up by your own bootstraps. It just doesn't work logically. Second, like we just said, that point isn't even a real thing in physics. And third, and this is a big one, where did all that energy come from? We're told energy can't be created from nothing, so what gives? And this is where we get this total mind flip, this new perspective. What if the universe isn't some magical thing that just popped into being? What if it's the answer to a really complex math problem? The solution to a puzzle that has a very specific set of rules, or what physicists call boundary conditions. And that right there is the heart of what's called the P-in hypothesis. The idea is that our universe didn't just appear out of nowhere from inside itself. Nope. It was kicked into gear by a blast of energy from outside, from some kind of external boundary. And what's so cool about this idea is that it just, poof, makes those three big problems we talked about just go away. And at the center of all this is one single, incredibly elegant equation. Seriously, look at this. You can think of it as the ultimate cosmic balance sheet. It's the simple accounting rule that literally governs why our space-time is even here. Okay, let's break this down. Pn, that's the total energy that got shot into the system from the outside. Now that energy has to go somewhere, right? Some of it, P out, is the stuff that stuck around. That's us, the stars, the galaxies. That's the energy that successfully became our universe. The rest, P lost, is kind of like the waste heat or the leftover bits that didn't quite make it into a stable form. It's just simple accounting. What you put in has to be accounted for on the other side. Okay, but wait, you're probably thinking the same thing I was. If you're injecting energy, what are you injecting it into? There has to be something there to receive it, right? What was the canvas before the universe was painted on it? So the theory suggests there was this pre-geometric state. They call it a phase field. The best way to picture it is to imagine a perfectly endless, perfectly still, perfectly uniform fog. Inside this fog, there's no here or there, no left or right, no concept of distance, not even time. It's just pure, raw potential, waiting for something to happen. So here's how it all goes down. Step 1, you have that uniform, boring fog of potential. Step 2, bam, the P-in energy injection hits it. It's the trigger. This wakes up the field, starts creating ripples and little differences in it. And then step 3, out of those ripples, like magic, the first particles and the very fabric of space-time itself start to condense, to crystallize into existence. Now this is a really, really big deal. You have to get this. In this model, space-time, the three dimensions and time, it isn't the stage that the universe plays out on. It's one of the actors. It's something that gets created in the process. It emerges from that deeper reality, kind of like how tiny water droplets suddenly appear and condense out of invisible steam. Okay, I get it. This is a great story. It's elegant. It makes sense. But is it science? I mean, for any theory to be taken seriously, it can't just be a nice idea. It has to make predictions that we can actually go out and test. So the big question is, does this P-in hypothesis have the goods? And the answer is a huge, resounding yes. Think about it. If you kickstart the universe with an energy blast from one side, let's say it's probably not going to be perfectly symmetrical, right? It's not going to be perfectly smooth. It could leave behind these giant cosmic scale, well, fingerprints. And those fingerprints could still be visible today if we know where to look. And this is where the rubber meets the road. This new idea makes predictions that are totally different from the standard story of the Big Bang. The standard model says the early universe should be super, super smooth. Pi says, nope, look for big, lopsided patches. The standard model struggles to explain dark energy. Pi says that's not some weird property of space, that's just the leftover background hum from the initial energy blast. They even predict different kinds of ripples in spacetime, gravitational waves, that our telescopes might be able to pick up on. Now, check this out, because this is where it gets absolutely wild. We've already found weird stuff out there that doesn't quite fit. The Planck satellite, which mapped the afterglow of the Big Bang, found some really strange anomalies. There's something they call hemispherical asymmetry, which basically means one half of the sky is slightly different from the other. And there's this bizarre alignment of giant cosmic structures that some astronomers have jokingly called the axis of evil. These things are huge puzzles for the standard model, but they are exactly the kind of fingerprints you'd expect to find if the P-in hypothesis is right. So you see, what we're talking about here isn't just another theory to add to the pile. This is a totally different way of even asking the question about where we came from. It takes us from this almost unanswerable philosophical question, what created the universe, and puts us on much firmer scientific ground. The new question is more like, okay, what are the rules of the game? What are the starting conditions and the energy inputs you need to end up with a universe that looks exactly like ours? It's a question we can actually try to answer with math and observation. And that's really the big takeaway here. Maybe our universe isn't just some random fluke, some accident that happened for no reason. Maybe, just maybe, it's the stable, predictable, and maybe even inevitable answer to a very specific cosmic problem. But of course, that just leaves us with one last mind-bending question to chew on. If our entire universe is the solution to a problem, well, that makes you wonder, doesn't it? What writes the problem in the first place? Something to think about. Thanks so much for joining me.